Hello, one. Welcome back to another session. Today, we're going to talk about the finite elements analysis. And in today's session, we're going to have a brief introduction on the basis of the finite elements analysis. And we're going to talk about the process of the design analysis using FEA. We'll practice FEA using CATIA version 5 and ANSYS Workbench, which I'm going to upload them on a separate file. We'll start the session by having a brief introduction about our FEA design process. What is actually FEA? And then we'll talk about the FEA analysis process, the wrong FEA examples, which are quite important to pay attention to the importance of having an FEA and once you applied wrongly. And also we'll do the couple of activities as I mentioned using CATIA and ANSYS Workbench. So hopefully by end of today, you will have an understanding of a basis of the design analysis, understanding the necessary logical steps of a design analysis simulation, and being able to perform the following tasks: a pre-processing, which is the finite elements modeling we call it, a processing, or let's say solution, and a post-processing. So let's go through the design process. This is a really overview of a design process. Once you have a design in your mind, you start working with the computer-aided designs and design into the software to be able to visualize it. And once you visualize that, in order to see how it's going to perform in reality, what you need to do, you need to make a physical prototype. Once you made a physical prototype, then you test it to see how it would be able to perform in reality. And based on the result you get, you come back and redesign it. So basically, you come back to the design stage again. It depends on how mature is your idea. You want to have different iterations to come back to your design and update it, make a prototype, test it again. If you are not happy with it, again, you come back and update the design, make a prototype, and test it. But there is an issue with this process. Just think about it. What's wrong with this process? I'm going to give you some time to think about it. What's wrong with the process? So the issue with this process is basically this process is costing. So it takes time to make that. So it's really time consuming as well. So it depends on what kind of products you are going to make. That will impact on the amount of the cost that you will have. For instance, if you are working with designing an aircraft or a car, every single elements of them needs to have a prototype to be able to test. And of course, once you put them together, again, you need to have another set of the tests. So for instance, a cost of a test, a prototype of the car might be over $1 million. Are the same things, for instance, a prototype for the fighter jets, usually they are over 500 millions. And once you test that, you don't want to come back to your line manager and say, okay, sorry, my design is not successful, so I have to come back again, design and make a prototype. So that's why the basically software developers, they come up with the idea of making a CAE, computer-aided engineering. With the computer-aided engineering, you would be able to use the computer-aided design geometry, a part you have, and make a virtual simulation through the software. Not only using the online and the software simulation, basically, using the computer-aided engineering would be easier, it will be faster and would be much more cost-efficient design cycle. Because I would be able to replicate that kind of scenarios virtually using a computer and to analyze my model. Not only it would be easier, faster, and cost efficient, it will actually open a door for much more creativity and innovation. Because with the first model that we used to use for the past couple of decades, I was limited to go with the options that I was somehow sure that what kind of results I would get from it. However, with the new using CAE, I can go with a much more creative approach for the approach I never done before because there is no risk. I can use the computer power to be able to replicate that model for me and to be able to study it, which is why the CAE is quite well known these days. But what is FEA? A finite elements analysis, or in short format we call it the FEA, is an engineering computational analysis that helps us to determine the strength of the product, which we can do it in a part or assembly level, in response to the loading which might be experienced in the operation environment. So basically, FEA simulates the behavior of real component or assembly with an idealized mathematical model, which we call the finite elements model or FEM, which includes the physical condition that's a part of product is going to operate. And in this method, we basically would analyze the model by the finite elements analysis solver, which would be the main core, the main brain of the computer, to use the calculations, the few mathematical calculations, and show us the result of how our product is going to perform in the boundary condition that we make. Or in simple forms, within the FEA, what we want to do, we want to use the geometry, the product that is we design, to replicate the scenario that we want to test it in reality using computer. So we want to make a virtual case to consider all the force that is going to be inserted into the model and how the model is going to perform in those real cases, but everything happens through the software. And in the FEA using the computer, we don't need to go through the mathematical equations. We want to use the brain of the computer, which in this case would be a FEA solver that has all the single kind of equation that's required for different kind of cases to go there and try to solve it for us. So that's a really powerful powerful tool to use, and it's really good for the engineers to make sure the products that they have, once they launch it, they will be able to perform in a long period of time with different kind of forces that's going to apply for it. But what type of the engineering analysis we have? Usually, if you ask somebody about the FEA, the person will refer you to the structural analysis. But we are not only limited to the structural analysis. Structural analysis is one of the most important parts and is one of those areas that lots of engineers they work on that to understand how your structure is going to perform under different forces. In the structural analysis, you can divide in two different formats, the linear models and non-linear models. Within the linear models, you're gonna use basically a product that you have and study the impact of the forces on the deformation and displacement that you get, depends on what material you used. For non-linear, it's the same sort of approach. However, because of the material you have, there is some sort of non-linearity. For instance, if you're using the elastic or viscoelastic materials, the kind of forces that will comes back to use wouldn't apply as a Newtonian rule. So for instance, if the Newton says if you apply an N, you will get the N back. Within the non-linear ones, you don't get the same N back. For instance, half of the N might goes to the force that is being exerted, half of the N might comes to the other area. That's why the nonlinear is really important. And every sort of product that we work with, there is some sort of approach of the nonlinearity to it, which going through the mathematical equations by how would takes a long time. However, the computer power would be able to become beneficial in here and study the nonlinear models as well. So that within a structural analysis, you would be able to define to the software whether you want to have a linear model or nonlinear model. But again, as I mentioned, you are not only limited to the structural analysis. You might also study vibrational analysis, which basically can test your structure or the product against the harmonic, random, or transient vibration, shock, and impacts. For instance, if you have an harmonic vibration after a period of time, for instance, the harmonic vibration would be applied to the car after a period of time, it will cause lots of issues for your basically frame and a structure to start breaking, to start get some sort of cracks because they are harmonic. And you would be able to analyze them using the FEA software as well. You might also study the fatigue. For instance, depends on how long is the life cycle of the product you have. There would be some sort of fatigue. For instance, you might work it as, for instance, let's say 5 years lifespan, 10-year lifespan, sometimes even 100 years. We have bridges that they are there for over 100 years. If I wanted to study it in a real time with a prototype, it takes a long time. And the beauty of FEA, I would be able to replicate that using a computer model to see how the product, how the structure that I have, how the part that I have would be able to perform in 10 years, 20 years, 100 years, and so on. What's going on? Whether do I get any kind of crack to the model, and how the fatigue gonna looks like after a period of time, which is why the fatigue analysis is really useful. You might also study the heat transfer. Within the heat transfer, if you have a flow through the model, you would be able to analyze it. What's the impact of that, the change to the temperature on the way the material is going to behave? And that's also really useful study. But let's talk about it, how FEA product is going to work. So FEA use a grid call, we call it mesh, and composed by nodes to solve the equilibrium equations. But let's talk about it. What do we mean by mesh? And why the meshing is really important, and why whenever we talk about the FEA, we hear about the mesh a lot. So I'm going to show you a really simple formula. If you have a square, and if you want to basically pull it toward yourself, that formula applies. So a force, that's the force that I'm going to pull it toward my side, and a stiffness, which depends on the material that I have, on the material that I'm going to use, and a displacement which I get. So once I pull it, depends on the stiffness of my material, I will get that U, which is displacement. So it's really simple in here. And by the way, this is a really simple formula. The FE is much more complex than that. I'm not going to go to the depth of the mathematical equation. This is just the idea for you to see how the FEA works. But I'm going to ask you a question. How about if I have a hook? How would you apply this formula and find out what's the displacement for the hook if I apply the same force toward it? Just think about it. I'm going to give you some time to think about it. Let's think about that for 30 seconds. And please note it down because we're going to talk about it. Great. So let's see what you probably guessed here. One of the ways that we can do that is basically I would be able to break my model to the smaller pieces, to the smaller square shapes, so I can still use this formula. This method, we call it discretization or a mesh generation. And every single of these basically squares, I can call it a mesh. So it depends on whether you have a 2D or 3D model, the way that the shape of the mesh would then change. So what you've seen on the previous slide was a 2D mesh, and now we have a 3D model. And to the 3D model, we have three different basically mesh elements. We have the hexahedral, which in hexahedral we have 8 vertices. We have tetrahedral, which we have 4 vertices, and we have pyramid, which have the 5 vertices. But which of these 3 mesh elements you think would be beneficial for your model, for your 3D geometry? Let's think about that. I'm going to give you some time to think about it. Some people might say hexahedral. One of the benefits of the hexahedral, if you have a simple 3D geometry within the hexahedral, I can basically cover the majority of the areas without any issue, which was by default, it was the mesh elements of the software for past few years. However, some software decided to use the tetrahedral by default, and the reason was if you have a product that has some sort of the curvatures, whether it's a fillet, whether it's an edge blend around it, you can see lots of product around us, they have a fillet and edge blend. Let's say the computer that you're watching myself right now, the phones or the tablets you're watching myself, the around of the area you will see a curvature, which we call the fillets. The reason we have the fillets around the products is basically you will be able to manufacture them easier because you will use the milling, for instance, machine or face milling machine. It would be much more easier to work with these curvatures rather than having sharp lines. But the problem is, if I'm going to use the hexahedral within the curvatures, I will get the torsion of the model. However, I can prevent that torsion by using the tetrahedral. And of course, if I go with a much more fine refinements in some sort of the tricky areas, I can use a pyramid, which if I put the pyramids on top of each other, I will get a really clean and mesh on the geometry that I have. So rather than I will have a solid answer that I'll always use the hexahedral, tetrahedral pyramid, the best answer is a combination of them. You might use the majority of parts with the hexahedral. Once you go to the curvature areas, you would be able to apply a local machine, local refinement, and change the shape of them, change the size of the elements. Also, whenever we talk about the mesh, we talk about the nodes. You will see that, for instance, in here, the different nodes that we have will make a one mesh. 1, 2, 3, 4, 5, 6, 7, and 8 nodes. We call these points nodes. So if in case you work with the softwares, sometimes you will have a control to control the number of the nodes that you will have in every single element and every single mesh. But let's go and then talk about it. The number of the mesh, or in better words, the mesh quality. Let's say I'm gonna divide or discretize the hook to the 1,000 pieces, and I will get the result. And now I'm gonna increase the number of the mesh and elements to the 1,000,000 pieces. Which one do you think give me much more accurate result? Think about that. Great. So the 1,000,000 will give you much more accurate result because the number of the mesh help me to apply those equations that I have to the different areas, which basically cover the majority area, all the area of the geometry that I have, so I will get a much more accurate result. How about if I increase that 1,000,000 to the 10,000,000? How about 100,000,000? So why wouldn't go by default to 1,000,000 from the beginning, or the 10,000,000 from the beginning? What would limit me to go there? The answer is a computer power. If I go to the much more refined mesh, I need a much more computer power to analyze it. Sometimes, for instance, to analyze the wing of the airplane, it might take around a month to apply a fully refined, a really good refined mesh using the high performance computers. So usually the people who works on the mesh, they spend a really long time to be able to analyze the appropriate size of the mesh, and they need the computer powers. So what you need to do, you need to decide based on how much computer power you currently have access to find the appropriate the mesh sizes. Also to find out that there are lots of scientists, they are working on the models, which we call the mesh independent models. So for instance, you would be able to increase the number of mesh in this hook and then get the result. Let's say 1,000, I'll get the result. I'll go to the 5,000, get the result. 10,000, get the result. 100,000, get the result, and so on. And I will keep continuing to increasing the amount of the mesh, applying a proper local meshing up to the time that from now on, if I increase the quality of mesh, if I increase the number of the mesh elements, if I go to the much more refined mesh, my result wouldn't change, which we call it the mesh independent model. A mesh independent model is the model that's your goal, which you want to work and use in industry. Because if you have a mesh independent model, you no longer need to go and make an actual testing, because your result would be completely accurate based on what you created, because you already have a really good mesh independency, which from now on, if you change the mesh size and qualities, you will still get the same result. And this takes long time. For some people, there have been years of working on that model, 4-5 years to work on a model to reach that mesh independent model. But what's the benefits of the using FEA? We already talked about that. It will help us to reduce the testing and redesigning costs. So therefore, we will shorten the product development time, which is really important. This is what will make it actually FEA a really good and useful tool in industry. Also, you would be able to identify issues in the design before you go to the manufacturing stage, which is really important issue, because you can come back to refine your model before actually become late. Because once you go to the pre-development and manufacturing, you're quite late. You cannot change your model at the time, because you already think about what model manufacturer you want to use and it's ready to go and to be manufactured. Also, you would be able to refine the design of the components before the components of the same system are already built. So for instance, if you're working with a full model, a car, it has a different elements of it. You would be able to refine your design as an element, as a part, without you having the need of the other components of the system. So whatever changes you will do, then it will impact on rest of models, right? Because they're going to be assembled on each other. Let's say if there is a cut area, if there is a hole area, and there is an extrude or a padding on the other area, if I change the diameter of this one, the other parts needs to be updated. And if I'm going to wait for the other departments to basically come up with their full design, it would be called late for me to update my design. So all the teams work together, make their design using the CAD, and analyze it using FEA to be able to make sure they're okay, and then continue to go to the next stage. Also, you would be able to optimize the shape before your prototype would be manufactured. As I mentioned, if you go to the pre-development stage, which basically will have a prototyping stage, it would be quite late for you to update your model. But whenever we talk about the FEA, we talk about three different stages: a pre-processing stage, a solution stage, and a post-processing stage. In pre-processing, you will start by having a problem definition. Within the problem definition, you need to have a geometry. You need to have a CAD model to be able to upload it onto the software. You need to also specify what materials you want to use. Materials are quite important because the property of the materials is important for the software to find out how your product is going to perform in different kind of the condition that it will make. You will need to understand how many loads, what kind of the loads, in what location you need to apply it. And also, what boundary condition? Is there any fixture that you need to have? If there any relation between the different components that you need to make, all of these things needs to be basically assigned to the products and needs to be defined through the software. Once you have everything, you go to the discretization. You need to discretize or break down your model to the smaller pieces, which we call it the mesh generation, this stage. And once you have everything in here, you'll go to the next stage, which we call it the solution stage. Within the solution stage, I have to tell the software what kind of basic analysis you want to do, whether it's a structural, fatigue, thermal, vibration, buckling, and so on. We already discussed about that. So I have to tell the software which of these I want to use. So based off that, I will decide what kind of solver, what kind of the mathematical equation the software needs to work with. And you can see that basically the equation and matrix will be defined. I have to tell the software whether I want to have a linear or non-linear analysis, because it would be again different kind of a solver and formulations and mathematical equation is required. Once I define everything to the solution stage, I will ask the software to go and solve the model with a solution, which every single software might use a different kind of a solver. For instance, some software like the ANSYS, they have their own solver, which are perfect, which are amazing. That's why the industry use that. Some of the other solvers, such as the Siemens NX, you have the options to not only work with the, for instance, NX Nastran, which is the Siemens one based on the Nastran, you will be able to use the other solvers, such as the ANSYS solver, the Abacus solver, and so on. So you will have an option to work with the other solvers as well. Once you solve the model, we reach to the post-process, which basically the main aim of FEA. You will now get the results. Within the result, you will be able to visualize it. For instance, you can get a plot out of it. You can make an animation to see how it's going to perform in reality. And now you need to interpret basically the result you get and write a report based on that. For instance, when is the failure area? What's the maximum amount of the stress that I have? What's the area that I will get the highest stress? And so on. But once you work with the FEA, because it's a computer software, a GIGO apply for that. A GIGO, the people actually are familiar with the coding, probably you're familiar with this one, which we call it a garbage in and garbage out. If you're working with the computer software, if you have a perfect model, however, you import the garbage data, a bad data, your result also would be bad, and a garbage result we call it. Let's say for FEA, you have a perfect geometry, everything designed perfectly. However, the forces I put, either they are wrong amount or either I put them in the wrong location. I haven't considered all the forces. The result I get is not accurate. I can, for instance, say this product is safe, go to the market, but it won't be safe. Or vice versa. I have all the forces, all the boundary condition, everything is considered perfectly. However, I don't have an accurate geometry, which is different with the one that I'm going to manufacture. The result I get is not accurate. So this one is really important. Usually if you work as a CAE engineer, you have the benefits of getting much more higher salary. In UK, usually it's between 20 to 30% more salary, which is really fun and it's become really good a skill which increase your employability. But bear in mind, you might people with the you might deal with the people's life. For instance, even the big companies that you see to the market, like Apple, they had the failures in iPhone 6 models that started to bend through the phone in the middle, which was due to the bad FEA because they haven't considered these forces and to update their design and update their structure into the design. In that case, we didn't have any basically impact on the people's life. But you might work and design a car, a bridge, and for instance, the Jacquard bridge, an offshore. If you have a bad structure, you're dealing with the people's life. And you will see, for instance, some of the examples, there are some of them, even if you work for a big company that's really hard to get the job over there, and I'm sure they are doing their job as best as possible, as high quality as possible, sometimes even they do the mistake. So probably you heard about the Deepwater Horizon oil spill, which was a disaster. And I highly recommend to watch the video that I'm going to upload it for you right now. And it's probably going to be on your screen right now. Click on it and watch that because you will see how they had a really good design to prevent these disasters, but they haven't considered all the forces and boundary condition. Basically, they haven't considered the changes to the pressure of the, into the model that they have, which act as a force, and then will get that disaster. For instance, a BP took $1.7 billion charge against due to the failures of the safety they had, as well as it cost them over $65 billion. So it damaged over 65 billion to the company. So sometimes a bad FEA causes lots of issues for the people. Lots of people might die due to that. So it's a responsibility for you as an engineer to make sure whatever product you release to the market, don't rush it, and make sure you consider every sort of aspects of that and then release the product. Great. So that was it today for just a brief introduction of FEA. And now what we're gonna do, we're gonna go through and work with the two different models. One of them is the angle bracket analysis, and the other one is the beam analysis using two different software. We want to work with the CATIA and ANSYS. So please pause this video and or stop this video and go and open the other video, which I'm gonna talk about how we can apply these FEA using different softwares, and we'll go through every single stage of that. I will talk about the pre-processing, a solution, and post-processing, which you will see all these softwares that will go through these three different stages, and they have different approaches to tell you what's the next stage and what's the next things you need to do. Thank you so much. That was it from me, and I'll see you into the next video.